time to continue our conversation about thermodynamics. So enthalpy is defined as the heat content of a substance at a constant pressure. Essentially, enthalpy itself, the value of H, you notice here that it has a symbol of an H. We don't really care about the heat content per se of the substance. What we really care is about the change in the heat content of a substance during the course of a reaction. So it may have started with a heat content, let's just use random values, of 2 and ended with a heat content of 10. That tells us that it gained 8 of these heat content values. We'll talk about units here in a little bit. That's what we care about. We care about what it does during its course of its change. Not where it started, where it ended so much, but what happened in between and how much energy was either given off or absorbed in order to do that. And so really what we care about is this right here, the change in H. Now you'll see an equation right here that we actually aren't going to use, because in order to use that, you'd have to know the heat content of your final products, that's the HF, and the heat content of your original reactants to be able to plug in and solve. We are going to solve for delta H, but not just not with this equation. This equation is one that isn't really useful because it's not possible to directly measure the heat content of substances. You have to take a bunch of factors into account. Excuse me. So it's not something that is useful for us, but we will have various ways that we will calculate delta H. We're going to learn a couple of them this unit, and then when we see thermodynamics again in the spring, we'll learn a couple of more. Now, one thing we do need to remember, and you did learn this stuff last year, this beginning part of enthalpy last year, is that if you have a positive delta H, then that means your reaction is endothermic, meaning it absorbs energy. And if you have a negative delta H, that means your reaction is exothermic, meaning it's giving off heat. That's going to be a really important fact that we need to ingrain in our brains now. So negative delta H is exothermic, positive delta H is endothermic. And again, we are going to calculate, we're just not going to calculate with that equation. Now, part of that comes into play with this next slide. I can get it up here. Oops, one too many slides. All right, this slide here talks about something called a state function. Enthalpy is something called a state function. There are a lot of state functions out there. Let me show you the definition first of state function. It says a quantity that is only dependent on the initial and final states of the reaction, not by the path by which they get there. So a state function is something that essentially can be calculated multiple ways and still get to the same end result. For enthalpy, enthalpy is one of those state functions. It doesn't matter what method we use. Remember, I just said a few minutes ago, we're going to use 2 different methods in this unit, and then in the spring we're going to learn a couple more methods to find delta H. It doesn't matter which method you use, you will get the same answer for the delta H, and that's because enthalpy is what we consider a state function. It might be easier for me to explain state functions using some other examples that would be a little more logical probably in your minds, because they're things we experience. So if you take a look here, I have 2 other state functions, things that would be considered state functions. The first one says the volume of a gas. So let's say you have a balloon and you want to put 1 liter of air into the balloon, and you blow it up immediately right to 1 liter. Okay, so you have 1 liter of air in the balloon. But let's say somebody else needs to put 1 liter of air in the balloon, and by mistake they put in 1.2 liters I have on your paper, or maybe 1.5 liters. They go past that. They can still have 1 liter of air in their balloon if they simply just let some of it back out, and then they'll end up with 1 liter. So all that mattered was that they started with nothing and ended at 1 liter. It didn't matter that you went straight to 1 liter and somebody else went past it and came back to it. That is a state function. Still ended up with 1 liter of air inside the balloon. A bank account would be another example. Maybe you get an allowance every week and you put in small deposits every single week into an account, and over the course of time you end up with $200 in the account. Okay, that's $200 in your bank account. A different example, maybe you got a check for $300 for your birthday and you spent $100 of it and then put the other $200 in your bank account. That's still regardless of what happened with the money, how you got it, it still ended up with $200 in your bank account. Those are state functions. Non-state function would be something like, you could see our two examples there, of distance traveled or time to travel. The time and the distance would not be state functions. I'm talking on here about going to New York, but let's use a different example. Let's say I wanted to go over to Sandra Day O'Connor. Not sure why we'd want to go to Sandra Day O'Connor, but let's say we wanted to go to Sandra Day O'Connor, and we could go out, Mountain Ridge's little driveway here. We could make a left onto 67th and go up north and hop on Happy Valley and make a right and travel to Sandra Day O'Connor. Okay, and that would take a certain distance. It would be, a couple of miles, however many miles that is. Or you could go out our little driveway and you could make a right on 67th Avenue. You could go down to the Loop 101 and get on the Loop 101, turn left, go on the Loop 101 around to the I-17, come north up the I-17, exit on Happy Valley, and then make a right into Sandra Day O'Connor. Did we still start at Mountain Ridge and end at Sandra Day O'Connor? Yes. But did it matter which path we took? And the answer, of course, is yes. And that means it is not a state function. State functions, the path does not matter. You still end up with the same final result from the same starting point. But with distance traveled, that is not the case. Time, same thing. It would have taken a very different amount of time to do our first plan to go to Sandra Day O'Connor than our second plan. So if you have the same beginning and end, and the path determines what's going to happen, then you definitely don't have a state function. If the path doesn't determine it, and it happens regardless of the path, you have the same beginning and end point, then that is a state function. Again, you can see in this equation that 2 moles of H2 are reacting with 1 mole of O2, and that when they do that, they make 2 moles of H2O. Well, the truth is they don't just make 2 moles of H2O. You can see here that you see the negative means exothermic, that they're also giving off 483.6 kilojoules of energy. The energy is like a product too. And so these delta H values are going to be given to us in the problem like this. And again, this equation relates to this delta H. It's like part of the coefficients. It's part of the values. You can also see that there's a second equation here, which is just the reverse of the first equation. So instead of making H2O, we're decomposing H2O. And if you notice, the only difference in the delta H is the same number, but negative and positive. Because if it takes energy to break up the H2O, then it's going to also release energy when it makes that H2O. All right, so the math. Now, hopefully you'll agree that the math is pretty easy. It's stoichiometry. So as long as you know how to set up a stoichiometry problem, you're not going to find this probably too difficult. It's just a new conversion factor, and the conversion factor is going to involve this delta H and then the coefficient for whichever substance it is that you're using. Now, I have the steps broken down here on the paper, but I don't want to do them as 2 separate steps, actually. I want to do them all as 1 step. So if you'll do all of this under step number 2, kind of combine these 2 steps into 1 math problem, because I don't want you separating it. It makes it more difficult. So you're going to start with what you know, which is that you have 454 grams of propane, C3H8. Okay. Then for every 1 mole, I'm going to convert this into moles. That's our first step. For every 1 mole of C3H8, if you look up the molar mass for C3H8, it is 44.0 grams. C3H8. So now at this point, I've gotten my gram value into moles. Now it wants to know how much heat is evolved from that specific amount. And I know in my equation, I'm looking at propane. So for every 1 mole, see there's a 1 here, every 1 mole of propane, along with all this other stuff, is going to make negative 220 kilojoules. So I'm going to make another conversion factor. I'm going to put moles, C3H8 on bottom, and I'm going to put kilojoules on top. It's not kilojoules of C3H8, just call it kilojoules because it's the kilojoules for the whole reaction, but it's related to the mole value. So look back here at the coefficient for C3H8, there's 1 mole. So for every 1 mole of C3H8, we get negative 2,220 kilojoules. And you notice that that gets your unit to where you need it. Please do not just assume that it's always 1 mole. It's the coefficient from that substance in the problem. So if I multiply this out and then divide and round to 3 sig figs, I'm going to get negative 22,900 kilojoules. So it's stoichiometry, just with a new conversion factor. Your conversion factor here is new. You get the kilojoule part from here. You get the mole part from the coefficient for whichever substance. So if I had used O2 in this problem, I would have had a 5 there. If I had used CO2 in this problem, I would have had a 3. If I had used H2O, it would have been a 4. So it's all dependent on that coefficient. Okay, so let's try another one. So this one starts us off with 15 grams of C2H6. They give us the equation. So for every 2 moles, that reacts with 7 moles. It's going to make 4 moles of CO2 and 6 moles of H2O. And then notice it also gives off negative 2,857.3 kilojoules. So we're going to take and start with our given, which is 15.0 grams of C2H6. We're going to convert first into moles. So for every 1 mole of C2H6, we have 30 grams of C2H6. Okay, that's the part we've been used to doing. Now it's our new conversion, because I need to go from moles of C2H6 into kilojoules. The kilojoule value comes from the delta H. Notice we're using kilojoules. Q is usually in joules, but delta H is usually in kilojoules. And then the mole value comes from the coefficient in front of that substance. So 2 moles of C2H6. You do all your multiplying and then divide, round, 3 sig figs. We get negative 714 kilojoules. Okay. Then there's some other notes there down at the bottom, just kind of summarizing some of the stuff we've said. Make sure you read through those and then do the homework problems. And I will see you guys on Monday.